Number 5 from the homework gave us a parametric equation, x and y, both in terms of t. And we are asked to find the first derivative and the second derivative. To find our first derivative, we need to find the derivatives of each of the x and y in terms of t. And then dy dx will be the y derivative divided by the x derivative. We learned that back in chapter 3, and then what's new in here is finding our second derivative. To find our second derivative, we want to take the derivative of this. So we want to do this thing prime, which needs a quotient rule. Low d high minus high d low over low low. Then we want to divide that by the original dx dt, which we can clean this up a little bit. In the top, distributing gives 12t squared minus 18t minus 6t squared. So I'll just change this to a 6. Over, then if I'm dividing by that thing again, it's really like I'm dividing by 3 of them. That might be able to factor down even more, right? 6. Nope, doesn't. Okay, it does. It just doesn't cancel. So that's where we'd leave our answer. Okay, so to find a first derivative, take the derivative of each and do the y derivative divided by the x derivative. To find the second derivative, take the derivative of your first derivative and then divide by the x derivative. The next type of problem asks us to find the points at which the tangent to the curve is horizontal and vertical. I'll do number 7 here. Because it's trig, that might be a little bit harder. So what is true about a curve when we are looking for either a horizontal or vertical tangent? What do we need?
A slope.
We need a slope, and a slope is a derivative. So we need to take our derivative. So 2 is a constant, it'll go away, so this derivative is negative sign. And the derivative of the y1, the negative 1 will go away, so the derivative is cosine. So our derivative is cosine over negative sine, and I'm going to leave it like that instead of simplifying that. Because if we are looking for where the curve has a horizontal tangent, what is true about the slope when we have a horizontal tangent?
0.
The slope equals 0. When does a fraction equal 0? When the top is 0. So I would set cosine of t equal to 0, and that happens at pi halves and 3 pi halves, etc. It didn't say between 0 and 2 pi, so etc. every odd multiple of pi over 2. Then the second part asks us where we have a vertical tangent. What is true about the slope if we have a vertical tangent? The slope is undefined. When is a fraction undefined? When the bottom is equal to 0. So that would happen at 0, pi, 2 pi, etc. And then the other type of question was arc length. Is there one in particular from 11, 13, or 15 that's more preferable to go over?
13.
15, 13,
I'm fine with any of them, really.
13, 15,
11.
11. I'm not going to do all 3 of them.
Just do 15.
15 looks the grossest to me.
Yeah, that's what I was going to say. Do 15. I didn't have a problem. The only problem I had with that one was opening my binder and figuring out what all that means. just got to a point where I jinxed it.
Yeah. I tried to, but my calculator hates me, so.
I thought about just typing in the derivative of that stuff and then stuff. But then I realized I can't do the derivative of secant in my calculator.
Okay, so we're asked to find arc length here. So arc length is the integral from a to b, square root of dx dt squared plus dy dt squared dt. So we need our derivatives of the two of these things. So dx dt has this ln of stuff. What's the derivative of ln?
1 over.
1 over stuff.
Times the derivative of stuff.
Chain rule times the derivative of the stuff. What's the derivative of secant?
Secant tangent.
Plus, what's the derivative of tangent?
Secant squared.
And then there's still a minus sign, so we need a minus cosine. Okay, so that took like almost the whole screen to write. So I'm going to simplify this guy before we move on at all. In that parentheses, I can factor out a secant, which leaves a tangent of t plus a secant of t. Which matches the bottom now. So this whole thing becomes secant minus cosine. Then I need dy dt, which is thankfully not nearly as gross, negative sign. Now we want to go plug it into this formula. So we're going to have the integral from 0 to pi thirds. They gave us those parameters. Square root of, and then I would want to take the x derivative, which is secant t minus cosine t, square that, plus negative sine t squared dt. And you can finite it.
How did you cross off the tangent and secant if it's addition on the top and multiplication on the bottom?
It's addition on the bottom as well.
Oh, it is?
Yeah.
Oh, okay.
Yeah, it's just a plus.
Did I? Pluses and t's.
I have a general rule. I just change all my t's to w's.
Pluses and t's.
You can just do t's capital.
I just put right on the top t is equal to w.
Yeah, you can do that on a free response. Make sure you do that, that you denote that you're changing a variable, but you can do that.
We can always switch variables, right?
As long as you denote that you're doing it. Like,
So
like
like
when I
change
put
x to y and not
you can just finite that the way it is. If you start to do some trig stuff on this, some nice stuff actually happens. When I square out this thing, I get secant squared minus 2 secant cosine, but secant cosine is just 1 plus cosine squared plus sine squared. So that becomes 1. So now I'm at secant squared minus 1. I have a square root of that. Secant squared minus 1 is actually a trig identity.
You have to have the plus side of it too.
No, I don't.
From the other side? From the y?
I canceled that with the cosine squared to make 1.
Oh, okay. Okay.
So there's the only trig identity that I have memorized is sine squared plus cosine squared equals 1. But we can manipulate this into the other trig function. So since this one deals with secant, secant is 1 divided by cosine. So I'm going to divide this whole equation by cosine squared. Which gives me tangent squared plus 1 equals secant squared. So in this problem, when I have secant squared minus 1, that's all equal to tangent squared, and I'm taking the square root of that, so that's just equal to tangent. So now I have the integral from 0 to pi thirds of tangent of t dt. Unfortunately, to integrate tangent, you need to do use substitution, so it still doesn't, in terms of
So what you're
integration,
saying
work
is
out
flip it.
wonderfully.
It's,
This could be a non-calculator question because you don't have to use your calculator on it. The likelihood of it is very minimal. But
Not one question, not one test.
the stuff before, like
you know,
5 through 9, is all calculator, right?
yeah, I mean, yeah, finding the derivatives would be no calculator. So like 1 through 9. On the arc length, you'd probably have a calculator on those.
And if you have a calculator, do very, very little of that.
Yeah, no.
Yes,
Yes. Well, get it to a point where you make sure you won't make a mistake.
right.
And then-
You get those the errors for the parentheses, and then you might want to look at something else. But
Are you supposed to be recording?
it is.
Make sure.
Thank you. Section 2 should be pre-calc review. In this section, we are reminding ourselves what vectors are. So if you have taken pre-calc and or physics, then this stuff should be something already of comfort for you. We're not actually going to do calculus on vectors yet today. We are just going to be doing a reminder of what vectors are, what they mean.
If you haven't taken pre-calc, why are you
I don't know vector, but I know
That's
pictures.
what I want to know.
I don't know what vector is.
Because you wanted
I
to
know
credit.
pictures. Frankenstein.
So, first example.
Huh?
I know pictures. I don't know.
I haven't taken pro class.
Vectors.
We're starting out with 4 points here, and our question says, show that the vectors u, which is defined as AB, is equivalent to the vector v, defined as CD. So there's two different notations we can use for vectors. One is a bold lowercase letter, so these u's and v's, when printed, would actually be bold. Can't really do that in handwriting too well, but bold lowercase letter is the way that we denote a vector, or as two letters with an arrow over it, but the arrow only does the top half of the arrow. It doesn't do the full point of the arrowhead. I don't know why. That's just the notation we use. And what it tells us is that we start at the first point and go to the second point. So if I put myself on some graph paper here instead.
They're each 3, 4.
A is at 0, 0. B is at 3, 4. So there is the vector u, or the vector from A to B. And then the vector from C to D, negative 1, 2, 3, 4, 2. And D is negative 1, 1, 2, 3, 4, 5, 6. And there's the vector V. For two vectors to be equivalent, there are two characteristics we need to check. The two key components are, careful with the word component because that means something else. The two key characteristics of a vector are its magnitude, which is its length, and direction. So if there are any Despicable Me fans in the house, a vector is a mathematical quantity with both direction and magnitude. And he calls himself that because he is committing crimes with both direction and magnitude. So a vector has direction and magnitude. So if these two things are the same, they should have the same direction and they should have the same magnitude. We measure direction by slope. So we'd want to confirm that these two things both have the same slope. So when we look at slope, we've got a rise over run of 4/3 and a rise over run of 4/3. So they have the same slope, which means they have the same direction. Second thing we'd want to check is that their lengths are the same. We could find their lengths by doing the Pythagorean theorems on those triangles we just drew and find they both have a length of 5. So because both direction and magnitude are the same for these are equivalent vectors.
Is it possible for them not to have the same length with a different rise over run?
It has double.
Yeah, I mean, it would be a multiple,
Yeah,
like,
I know you could have
I mean, you
like
could have a rise
6
of
over
8, 6, and that would make a longer vector, so they
Yeah.
could have same direction but not
That's why I
magnitude.
use the term rise over run instead of slope.
Right, right.
So rise
Yeah.
over run, no, but slope, yes.
Right.
Okay.
Does for a vector, does it always go from its first point A to its
Yes.
second point B?
Yep. Yep, direction matters, that we start at the first point and go to the second point. The first point is called the initial point, and the second point is called the terminal point. Second example. Second example says find the component form and length of a vector, PQ, which goes from P is -3, 4 to Q is -5, 2. So if I plot out this vector, PQ, I get this. A component form means that it begins with its initial point at the origin. Okay? Component form means its initial point should be at the origin. So what we want to do in this problem is think about like a geometry transformation, and how do I get point P, the initial point, to the origin? Well, I would have to move it over 3 and down 4 spots if I want to relocate it. But if I'm going to do that to point P, and then we usually call it like P prime, if I want to do that, I need to do that same exact thing to point Q and move it over 3 spots and down 4 spots. And we'll call that Q prime. And this new vector should have exactly the same magnitude and direction as the original one. We've just relocated it. And when we relocate it with its vertex at the origin, we have a new way we can name it. We are going to name it
Steve.
with its x coordinate and then y coordinate of its final point. So its terminal point is at -2, -2, and that becomes its vector name then, is -2, -2, but with pointy brackets instead of round parentheses brackets to be a point. We cannot call it Steve, no.
We can't put in the brackets -2, comma -2 is equal to Steve.
No.
Can I call you Travis?
No.
Can we put 2 equals
Okay.
S times
Part B.
No.
Let's move on.
Yeah, let's move on.
Part B wants us to find the length of this vector.
Joke's over.
To find the length of a vector, make a triangle out of it, and find the Pythagorean theorem on it. 2 squared of 2 is the length or magnitude of this vector. The notation for magnitude is absolute value. The notation for magnitude is absolute value. So when you see an absolute value around a vector name, it is asking for the length of that vector, which is found by the Pythagorean theorem. If the vector has a length of 1, we call it a unit vector. So we could turn this into a component unit vector by taking the vector it is and dividing each part of it by its length, and that will create a length of 1. So this is a component vector because it begins at the origin, and it is a unit vector because it has a length of 1. So we take the vector as is, the component vector, and divide it by its magnitude, and that will give it a length of 1.
So that's a component unit vector?
Mm-hmm.
Can unit vectors not be component vectors?
Yeah, you could have any general vector that only has a length of 1,
Okay.
but usually we want it in component form when we're talking about it. Usually they kind of go hand in hand, but you could have a vector with length 1 located anywhere.
confused as to what we just did.
We made it into a unit vector, so it just has a length of 1.
How does that have
So-
a 1?
I guess I shouldn't really have an equal sign here because they're not really equal. This is a unit vector because it had a length of 2 square root of 2, and I divided by that length,
Right.
which would now give it a length of 1. If I would reduce these down,
I was about to say, can't you reduce it?
if I would reduce these down and do a Pythagorean theorem on that now,
What's a half plus a half?
I should get an answer of 1, which means this thing has a length of 1. And that's what we call a unit vector, is a vector
Yeah.
with length 1.
And also you could say that like because the lengths were originally -2 and -2, and they were put on top, and so then when we reduced it down, they became
Right.
-1 and -1.
Yep.
And that, the vector can go in any direction. It could be -1, 1, 1.
Yes, it could go in any direction into any quadrant.
As long as they're the same price.
The next question, we're going to need some trig. Find the component vector with length 3 that makes an angle of 40 degrees with positive x-axis. So graphically, I want to be at a 40-degree angle, and I want to have a length of 3. So, not drawn scale.
Okay, good.
A scale, maybe, but not like the scale of the graph paper and each square being 1. How would I find, since we name a component vector by its x component length and its y component length, how would I find those x and y values here?
3 cosine of 40 and then 3 sine of 40.
Trig.
Dang, dude, that was fast.
Do this all the time.
I
So,
was already thinking about it.
if in a triangle cosine is equal to opposite, or cosine is equal to adjacent over hypotenuse, then the cosine of 40 should be the adjacent over hypotenuse, or that side would be 3 cosine of 40. Or sine of 40, and I would multiply by 3. We are in degree mode here currently. This is maybe 2 sections of the book that you're going to have to switch your calculator to degrees for.
Wait, this can't be.
So our component form would then be the x value, which is 2.298, and the y value,
Whoa.
1.928.
Okay, my calculator automatically switched to degree. I don't know why. It just does that.
So we want to be in degree mode for this section and the next section, and that's about it.
I don't know how this happens. I would watch out for that on the test. I would
Yeah.
I
Yeah.
watch out for it on every test because I never know what's going to pull
My
a fast one on.
My old calculator used to be able to like
That.
somehow be able to detect whether or not if I wanted it in degrees or in radians. Because whenever I would
That's what Kyle's doing.
I'm gonna do
Yeah,
that.
Kyle's doesn't do it when he wants it.
I was gonna say,
Just
my
randomly
old
does it.
calculator used to do that. It would just always give me the wrong one.
Alright, so that was examples 1, 2, and 3. We didn't have any notes on those. Now getting into section B, vector operations. Adding, subtracting, multiplying vectors by a scalar, or multiplying them by -1. We can just take care of our component-wise operations. So if we're adding, we can just add the x parts, add the y parts. Subtracting, subtract the x parts, subtract the y parts. Multiplying by a scalar, which means just a plain number. So not a vector times a vector, but just a number times a vector. Just multiply each part by that number. Multiplying by a negative, we'll change it to the opposite direction, but keep the same length. It just multiplies each part by a negative. So these properties of vectors, addition is associative and commutative. So addition, it doesn't matter whether you do a plus b or b plus a. For commutative, you can also group them. Scalar multiplication is associative and distributive, so you can distribute it through things. So they follow kind of our normal rules of real numbers here. So if u is defined as -1, 3, and v is defined as 4, 7, we want to find 2u plus 3v. 2u, I would take the u vector and double each component. 3v, triple each component of the v vector. And then to add them, add component-wise. What this is doing pictorially, and I would not draw this, I can't even really draw this out, but it's taking this u vector, -1, 3, and it's multiplying by 2. Multiplying by 2 only changes the magnitude, it does not change the direction. So it's taking how long this thing was and doubling it. Okay? Then we're taking the v vector, and when we add vectors, we add them end to end. So from the end of this now, I'm going to put the v vector, which has a value of up 4 and over 7. So I don't know, I'm just pretending, something like this. And then I'm going to double that.
Isn't it triple that?
Triple that, yes, thank you.
Oh, okay.
And our final answer should be from start of the first one to end of the last one.
So
Yeah.
you don't want to do like both scalar multiplications first. You want to do the first one first, then graph that, and then do the second one from where that one starts.
Right. Yep. Because the adding has to go end to end, so we have to figure out where the end of the first one is before we can start building the second one.
Well done.
All right. So that's the idea of vector addition pictorially. If I wanted to do u minus v, I would just take the u vector and subtract from it the v vector. So -5 and -3. Thank you. It's always the easy ones. And part C of this question wants us to find absolute value 1/2 u. Okay, so first, 1/2 u. So I take the u vector and multiply it by 1/2.
-1/2.
Yes, I was thinking ahead to the next number.
Oh.
And then how do I take the absolute value of a vector? What does absolute value mean?
Get rid of the negative.
It does not mean get rid of the positives.
How far away it is from 0.
How far away it is from 0, which as a vector means the magnitude, which is the length, which is
that squared plus that squared, the square root of
Yes.
the
that.
Pythagorean theorem.
Oh. Wow.
I wanted to say that, but everyone was shouting different
One
things.
time I had a program
I think
for
I
it.
need my voice.
I don't think that's
In
right.
case
No.
I don't have program
I'm a
for it,
peacock,
so
I
I
need
need
to
to
fry.
already know the magnitude and angle, so.
Okay.
I'm gonna step
So,
back.
absolute value means the magnitude or the length of the vector or the distance from 0, since they're component vectors. And we find that by doing a Pythagorean theorem on its components.
Okay.
The next part of the notes, the angle between vectors, I don't care about.
Me
So
Me neither.
we're gonna skip that because I don't care about it.
Hey, jump front.
Would it be on
We
like
don't
the
care
test?
about
No,
it, then we.
that's why I don't care about it.
Okay. That's a good choice. Good.
Thanks for your word of confidence there. I do care about applications. I do care about applications. That's where we could see some problems come up. So example 6
I do too, because a lot of them have to do with stuff you can throw.
says find unit and normal unit tangent
Okay.
and unit normal to the curve parametrized by this at the point where t is 4. All right, so to find a tangent line, what do we need?
Slope.
A slope and
Point.
a point. Okay, so we're going to begin by finding our derivative. We learned parametric derivatives in the last section. So we're going to do dy over dx. dy is 1/2 t to the negative 1/2. dx is just 1/2. So this all turns into 1 over the square root of t, which at t equals 4 is 1/2. So the slope of our tangent is 1/2. Now, since we are talking about vectors, a slope of 1/2 means rise 1, run 2, and we're talking about this vector. How would I find, since it says we want the unit vectors that are tangent and normal, I need to divide by the length. How would I find the length of this thing? Pythagorean theorem. So the Pythagorean theorem on this thing gives a square root of 5.
Oh, it goes so fast. Oh, makes sense.
It's just 1 and 2.
1 plus 4.
So before taking the unit part of this thing, its endpoint was at x is 2, y is 1. Now we want to turn this thing into a unit, so we're going to divide by its length. And that is one vector that is going to be tangent to the curve. There is another vector that will also be tangent to the curve because
Negative both of them.
it could go that way. Right?
So plus or minus?
So plus or minus both of them.
Yeah, when you're doing plus or minuses like this, it has, when you're plugging it in, it's either both all the tops or all the bottoms, right?
Yes,
You can't, like,
right.
something.
Now for the normal. What do we know about normal and tangents?
They're inverses.
Reciprocal slope and opposite.
Opposite and reciprocal. So if we were working with dy dx as 1/2, we now want to be working with negative 2. So pictorially, that is down 2 and over 1. So now our vector looks like this. So that endpoint is x is 1, y is negative 2. It has the same length as the other one.
But now it's flipped around.
It's just going in a different direction.
And plus or minus.
And it could also be going in that direction. So we need to plus or minus this, but this brings up what John was talking about. We have to be careful with our plus or minus. If I do plus or minus on this first one, I actually want minus or plus on the other one, so that they're always opposite signs of each other. The last example is a very physics example. A Boeing 727 plane flying due east at 500 miles an hour.
The one that was lost.
Those
You
are
found it.
770s.
It was in the ocean.
In still air encounters a tailwind.
I'm absolutely sure they have to stop it.
Encounters a tailwind at 70 miles per hour acting in the direction of 60 degrees north of east. Instead of placing this at the origin, I'm going to place it at the end of my other vector. So I'm going to have 60 degrees here, and it's going to have a length of 70.
What?
The length is representing the speed. So we've got 500 mile an hour plane going east, and then a wind going 60 degrees north of east at 70 miles an hour.
So where'd you place that? 500?
at the end of the 500.
Okay.
Our plane then is going to change route. And the question is, what angle is it actually going to be heading at now, and how fast is it going to be going? So how fast it's going to be going is our magnitude of this thing, and what angle is it going to be going is the angle down at that corner. What we're going to do is build this thing from two different vectors. So I have one vector that only has a horizontal component of 500. And then I have another vector that has both a horizontal and vertical component. The hypotenuse is 70. How would I find the horizontal component here?
70
I'm going to need a cosine.
Yeah.
So
70
cosine of 60 is going to be equal to adjacent over hypotenuse. So that x is going to be 70 cosine of 60. And the y likewise would be 70 sine of 60. Together, these make one big triangle that has a horizontal component of 500 plus the 70 cosine of 60, which is 35. So that is
Are we
535.
Are we gonna have calculators for that?
It's 60 degrees, so I hope you don't need one.
Just
30, 60, 90 triangle.
Yeah. Just
Mm-hmm. And our y component is just figured by the wind because the plane was going horizontal. So we get that 70 sine 60, which is 35 square roots of 3. We want to find how fast the plane is going, which is the magnitude of this. So how do I find magnitude?
Squared, squared, squared. Oh, squared, squared, plus squared.
Which is called.
Okay, you would have a calculator for this.
I would hope so.
What? No.
Okay, so the wind is helping out the plane here, helping it gain some speed.
And some height, maybe.
And we want to find the angle. How would we find the angle?
You would take that and
Tangent of the two numbers we have.
Okay, so since this is a right triangle, we don't need law of sines or law of cosines. We can just do it with regular trig. If we're talking about the opposite and the adjacent, we're talking about a tangent. So the tangent of that angle is the opposite over the adjacent. An inverse tangent, that guy, and it's 6.5 degrees.
just has to put one on top, one on the bottom. The bigger one, choose the bigger one, the smaller one, choose the smaller one.
For your homework, I don't think there's any problems that I need to delete and other stuff, so.
You can keep them all with that.
What all those things are.
But all I think I might do 6 extra.
All the sines and cosines are different numbers.
Yep, you're good with the homework assignment that's there. The part that we skipped doesn't come up in any of the problems, so.